This is the second video for Chapter 13. We're going to talk about types of error that we can make in hypothesis testing and power. So remember, the p-value is measuring how strong the evidence is against the null hypothesis. And it does it in kind of a funny way. It measures how likely we'd be to see our test statistic if the null hypothesis were true. So when the p-value is small, it gives us stronger evidence against the null hypothesis because it's indicating that our sample is not very consistent with the null hypothesis. On the other hand, when we have a larger p-value, that gives us weaker evidence against the null hypothesis because it's an indication that the sample data are not unlikely to have happened if the null hypothesis are true, or that they are consistent with the null hypothesis. So smaller p-values are stronger evidence against the null hypothesis. Now, often we said that we choose a significance level, which is a threshold, that's used to determine whether to reject the null hypothesis or not. And so if we set the threshold at 5%, then if the p-value is smaller than 5%, we say the evidence is strong enough to reject the null hypothesis, and we have a statistically significant result. On the other hand, if the p-value is not smaller than 5% here, then we say the evidence is too weak based on our sample to reject the null hypothesis, and the result is not statistically significant. Now, when we're drawing conclusions from hypothesis tests, it's important to remember that what we're doing is we're using data from just a sample to try to make our best guess about what is true in the whole population. And when the p-value is small, we reject the null hypothesis. We say the observed result was statistically significant because it was unlikely to have happened if the null hypothesis were true. But it's important to remember that unlikely to have happened does not mean that it was impossible. And so, based on the truth, which we may never know, and by that I mean what is actually true in the population, our conclusion that we've came to from our hypothesis test could be wrong. So even if we conduct the test 100% correctly, there's always the chance that our sample is a strange sample that didn't give us a correct decision when it comes to understanding what's true in the population. So let's talk about errors that can be made in hypothesis testing. First of all, we need to remember that when we draw a conclusion of a hypothesis test, we will either reject the null hypothesis or fail to reject it. And then, of course, there's reality. The truth is that either the null model is false and the alternative is true, or that the null model is true. Now, if we reject the null hypothesis and it's actually not true, then that's a correct decision. But if we reject the null hypothesis and it turns out that the null hypothesis was true, then that's an error, and that's what we call a type 1 error. So type 1 error is rejecting the null hypothesis when the null was true. How about when we fail to reject the null hypothesis? Well, if we fail to reject the null hypothesis and the null hypothesis was actually true, then that's a correct decision. But if we fail to reject the null hypothesis and it's actually false and the alternative is true, then we've made an error, and that's a type 2 error. So type 2 errors are failing to reject the null hypothesis when the null was actually false and the alternative is true. So I'm going to take just a minute and think about what these errors would mean in a context. So first of all, look at an example comparing weights of male and female guinea pigs. I'm going to test to see if there's a difference in mean weight between them. So the null hypothesis will be that the mean weight among male and female guinea pigs are the same. And the alternative is that the mean weight differs between male and female guinea pigs. Take a minute, stop the video, and think about what it would mean to make a type 1 error in this situation. Okay, a type 1 error is rejecting the null hypothesis when it's actually true. In this situation, that would mean that we find statistically significant evidence that the mean weight differs between male and female guinea pigs, when really they're the same. Okay, same situation, but now think about what it would mean to make a type 2 error. Stop the video, think about what it means, and then turn it back on. A type 2 error, remember, is failing to reject the null hypothesis when the alternative is true. So this would mean that we did not find statistically significant evidence that the mean weight differs between male and female guinea pigs, when really they are different. So I'm going to take a minute and talk about how we control type 1 error. When the p-value is small, less than the significance level, we find that the observed result was statistically significant because the chance of seeing our test statistic, if the null was true, was less than the significance level. So what that means is that we're finding a statistically significant result if the null is true, not more often than this significance level. And so what we can think of the significance level as being is the sort of acceptable risk that we're willing to take of making a type 1 error. And so if you were to choose a level other than 5%, it should be based on the sort of relative importance that you think there is of making a type 1 error. If you think it would be especially bad to make a type 1 error because of what that would mean in context, then you may decide to use a slightly smaller level of significance. On the other hand, if you think that there's very little downside to making a type 1 error in your particular situation, you might decide to use a slightly larger level of significance. Next, I'm going to talk about the idea of statistical power, and then we'll look at a simple example of calculating the power. So power is the chance of rejecting the null hypothesis when the alternative hypothesis is true. Now, since the probability of type 2 error would be the chance of failing to reject the null hypothesis when the alternative is true, those are complements of each other, and the power is equal to 1 minus the probability of making a type 2 error. The power depends on the specific value within the alternative hypothesis that turns out to be true. The farther the truth is from the null hypothesis, the more power we'll have to detect that difference. If the truth is very close to the null hypothesis, it will be hard to detect that difference. It also depends on other things, including sample size, the significance level of the test, and the amount of variability in the population. And we'll see a little bit more about sample size at the end of the video. So when we want to calculate power, there are kind of two major steps that we have to do. The first one is to create a null model. A null model is a probability distribution of our sample statistic, assuming that the null hypothesis is true. Once we have that distribution, we use it to figure out a rejection region. That is, what values of the test statistic would lead us to reject the null hypothesis. Once we figured that out, we create a second model, an alternative model. It's the probability distribution of the sample statistic, assuming a specific value for the alternative hypothesis. Then we figure out what proportion of that alternative model is in the rejection region that we found up above. Calculating power usually requires us to make some assumptions, and we can either use a mathematical model or a simulation-based approach to calculating power. In this video, I'm going to use a mathematical model to do it. So an example we're going to use is, does birth weight of babies born to smoking mothers differ from the general population? The average birth weight among full-term babies born in the United States is 7.7 pounds, with a standard deviation of 1.1 pounds. The null hypothesis is going to be that the mean birth weight of babies born to smokers is the same as the general population, that the mean is equal to 7.7 pounds. The alternative hypothesis is going to be that the mean birth weight of babies born to smoking mothers differs from the general population, that is, that the mean is not equal to 7.7 pounds. Now remember, our first step in finding the power is going to be to focus on the null model, but first I'm going to need to figure out what kind of alternative hypothesis I'm interested in and get a little bit more information. So suppose that I take a random sample of n equals 30 babies born to smoking mothers. Okay, so I know my sample size is n equals 30. I'm going to conduct my hypothesis test using a 5% level of significance. The significance level is something else that I said affected the power. And I want to know how much power will I have to detect a difference if the true average birth weight is 7.2 pounds. So this is going to be our specific alternative that we'll need for part 2. Okay, so first to set up the null model. The null hypothesis is that the mean birth weight among babies born to smoking mothers is 7.7 pounds. Things that I know the significance level is 5%. I know the sample size is 30. And I know that the null hypothesis mean is 7.7. Something I don't know, but I'm going to need to make an assumption about, is the standard deviation of birth weight among babies born to smoking mothers. Now, I do know that in the population of general population, the population standard deviation is 1.1. Since I don't have any better information, I'm going to assume that that's the case among smoking mothers also. So now I have the assumptions that I need, and I've thought about what I know, and I'm going to use this to create a null model. Now my sample statistic is going to be the sample mean. So I need to know how the sample mean is distributed if the null hypothesis is true. So if the null hypothesis is true and my assumption about the standard deviation is true, then I know that the sampling distribution of the sample mean x bar, because the sample size is relatively large at 30, should be approximately normal. And that the mean of my sampling distribution should be equal to the population mean. And that the standard error of x bar should be equal to sigma over the square root of n. So if the null and the assumptions are true, that means that the sample mean x bar has a normal distribution. The mean of that normal distribution will be 7.7 pounds, and the standard error is going to be 0.2 pounds. Next, I'm going to figure out a rejection region. My significance level is 5%, and my sampling distribution is normal, with a mean around 7.7 pounds and a standard deviation of 0.2 pounds. My significance level is 5%, which means if my p-value is less than 5%, I'll reject the null hypothesis. Now, since I'm doing a two-tailed test, looking for a not equal to, that's going to be, I'm going to have reject if I'm beyond the point where I have 0.025 in the upper tail, or below the point where I have 0.25 in the lower, 0.025 in the lower tail. Because if I get a value in either of those ranges, when I double the area beyond it, I'm going to get a p-value that's less than 0.05. So now I can figure out these values. This is going to be 97.5 quantile for my normal distribution. This is going to be the 2.5 quantile. And I can find that those are 7.31 and 8.09. So I'll reject any time I have a sample mean that's above 8.09 or below 7.31. So those are called my rejection region. Okay, so now that I know my rejection region, I'm done with my null model, and I need to start thinking about my alternative model. So my alternative model is going to be based on my alternative hypothesis. And remember, it's going to be the chance, I'm going to be setting it up around a specific alternative. And I want to know what the chance I detect a difference if the true average is 7.2 pounds. So this is my specific alternative. And so my alternative model is going to be assuming the specific alternative is true. Now, what I know the sample size is 30. That's going to be important for understanding how much variability I'd expect to see in this alternative model. I also know that the specific alternative hypothesis is that the mean is equal to 7.2. Assumptions that I need to make. Again, I need to make an assumption about the standard error, standard deviation of the birth weights among babies born to smoking mothers, and I'm going to use the same assumption that is equal to 1.1 that I did in my creating my null model. So once I've done this, again, my sample size is big enough that my sample statistic x bar should have an approximately normal distribution. With its mean at 7.2 pounds and standard error 0.2. So once I've got my alternative model, now I need to figure out what proportion of the distribution in my alternative model is in that rejection region. So remember, we said if the alternative hypothesis and the assumptions are true, then I've got a sampling distribution for my sample means that's centered around 7.2. I want to figure out what's the chance that I'm going to be at 7.31 or below, because I'd be rejecting there, or at 8.09 or higher. Remember, those are my rejection regions. Right, so these two pieces together are going to give me my power. So looking at my normal distribution, I can find the probability of the mean being above 8.09 in this distribution is 0.000004 approximately. The chance that so I've got a tiny little area out here. The area that it's less than 7.31, that's this area here, is approximately 7.708840. So altogether, if I add those two areas, I get 0.708844. So the power of the test is approximately 71%, which means that if the true mean birth weight among babies born to smoking mothers is 7.2, then with a sample size of 30, testing with a 5% level of significance, there's approximately a 71% chance that I would actually detect that difference, which leaves an approximately 29% chance that I would end up making a type 2 error. Next, I'm going to talk about how sample size is related to power. So I'm going to start by drawing an axis here, and I'm going to just give it a quick label. Guess that's all I need. Okay, so remember, when we had a sample size of n equals 30, our standard error was 0.2. And to find the power, what we did is we said, okay, I've got this null model with a mean of 7.7, and I found my rejection regions down here. And then I said, okay, if the alternative is true, then the mean is really at 7.2. I'm going to have a distribution with a similar amount of spread, so something like this. And then I figured out what proportion of this distribution, this alternative distribution, was in the rejection regions, and that gave me the power, and the power was about 71% power. Now, let's think for a minute about what would happen if instead of a sample size of 30, I used a sample size of 100. The standard error, 1.1 over the square root of n, is going to be 1.1. So it's got a much smaller standard error with a larger sample size. What this means is if I look at my distribution in this situation, kind of imagine the same scale up here, my null distribution is going to be centered around 7.7, but it's going to have a lot less spread than the old one did. It's going to look more like that. Half as much standard error almost. I'm still going to find my values where I'm going to reject. There's my rejection region. You can see I start rejecting for things that are closer to the null hypothesis than I did with a larger sample size. Then my alternative distribution, centered at 7.2, would also have a lot less spread. So I'm going to have something like this. And if I look at the proportion of this distribution that falls in the rejection region, see, I've got all of this area. And so my power is going to be much larger. And this happens because with a small sample size, there's a lot of overlap between the null and alternative distributions. With a larger sample size, my standard error gets smaller and there's less overlap. So generally speaking, larger sample sizes will give you greater power. Before the live meeting on Thursday, please read Chapter 13 in the textbook. It takes a very Verbal and not mathy approach to introducing hypothesis tests. It's definitely worth a read, but I also wanted to do the video in a different style to make things a little bit more concrete, so I hope that that's helpful. Also, complete as much of homework 8, which is due Thursday night, as you can, so that you know what questions you have about it when you come to the live meeting on Thursday. And work on the chapter 13 exercises for Thursday's class. Thanks, have a good day.